So it'd be a good way to investigate both, if you know what I mean, I think. But still, see what you feel like at the end of this. This may have been enough. So what you always have to do when you talk about geology, and I'm not going to make a big deal of this, is the time scale. You've all been to talks, I think, I'm sure, where they mention the fact that it's a huge time scale, a bit just like just now we were talking about the universe and difficult to comprehend the time scale. But we can do this because we can deal with big numbers. We often talk about nanotechnology, and it's just in the other direction, that's all really. So I've given you this chart. Don't try to remember all the different ages and the eras and so on. Again, most of these words you have heard before, I'm sure. But the important thing about the chart really is that in lots of books, they use the analogy of a year because we can kind of comprehend that more easily. So what this does, starting on the left, this compares the age of the Earth with a year. So nothing much happened for a long time. You know, the Precambrian was thought to be, you know, not much going on, just the rocks forming and the shapes and various things settling down. Life and all that kind of stuff got going, well, at the Cambrian, the so-called Cambrian explosion, 500 million years ago. And I'd never spotted this before, but this, of course, is why the ages have got the word Zoic in it. That hadn't struck me before that meant to do with life. So we've got the Paleozoic, which is old life, and then middle life, and then new life. And that was all very well until some school child found a fossil in some Precambrian rocks in the Midlands and took it into school, and they said, no, that can't be a fossil. But after a bit of argy-bargy, it was agreed that it was a fossil. So now the Precambrian, if you move into the right-hand column, the Precambrian now has a Proterozoic part. That's a fairly recent addition, because basically we keep finding life that's older than we thought. And that's a fascinating topic in itself, but which we'll touch on, I guess. So those are all the ages anyway, and we'll talk about what went on during them, I think. Because we're talking about the formation of the Earth, we're going to mostly be in that red piece. One thing that I thought was interesting is that we're pretty much sure that the Earth is 4.5 billion years old now. And if you're like me, you're thinking, how do they know that? And it's because of radiometric dating of rocks. The oldest rocks they found in Australia is the current set of oldest rocks. Are that old, and they do it by looking at the relative ratios of uranium and lead, for instance, things that where we know the time it takes for them to break down and change. And then they had another smart idea, thinking that probably the solar system's about the same age as the Earth. They analysed some moon rocks, got similar figures. So we're fairly confident we're looking at 4.5 billion years. What struck me as interesting is that's a third of the age of the universe. Again, something I hadn't, it's obvious, but I hadn't really thought about it before. So, and we think our sun's about halfway through its life, the sun being roughly the same age as the Earth. So if that means, you know, if our star is going to last 10 billion years, and in a minute we're going to look at how the solar system formed, and we know that all the elements we've got were made in stars, exploding stars. How come there's been enough time to create all those elements that we find on Earth? So just hold that thought as we continue. You probably know the answer, actually, if you've just watched Brian Cox explaining the solar system to you. But yeah, that's the time scale. The takeaway, as people like to say nowadays, is that although geological processes are very slow, there's been plenty of time for them to happen. And this was one of the things that held up geology for a long time, because people couldn't believe the Earth was as old as it is. I've got one one slide on life, because we can't really talk about geology without life. But the interesting thing is that starting right at the bottom, the so-called last universal common ancestor, and this isn't something that's been found or detected, this is a theoretical projection, backward projection, goes right back to the Hadean period. So 4 billion years ago, we found fossilized bacteria just after that. Well, just after, relatively speaking, in March compared with January. And you can read this yourself. So we had bacteria, we had algae, fossil algae. First animals just before the Cambrian explosion, and these are the sort of fossils that people have found now in Precambrian rocks. And then fish, things with legs, dinosaurs, mammals. And right at the top, partly hidden on my screen, you can only see his legs, one of us. As you knew, we're really recent. But life itself, the more research is done, the older it gets. And when we look at the state of the world, then it's amazing, really, that the only stable thing on Earth really was the oceans then. So this is before all the big ice ages and snowball Earth and all those kinds of things. But somehow life survived through all of that. Okay, so far?
Mm-hmm.
I wanted to quote The Age of Humans, but it's difficult because it depends when you define a human. Humanoid, certainly a few million years, whereas I think Homo sapiens are hundreds of thousands, something like that. Long enough, you might think, but still recently in comparison. One thing I should mention before we go any further, that book you recommended, Pat, I've constructed this presentation in a different way to normal. All the pictures come out of this book.
Yeah.
They're not stolen from Wiki at this time, because although it's what it says, it's for walkers, and it was the real idea of the book is to explain how to interpret geological maps. The first third is basically an introduction to geology, and I thought that was rather good because it's explained, it's got good pictures and explained, I thought, fairly simply. You'll have to see. So I thought I'd better put the acknowledgement in early on, so we know. So okay, let's talk about the birth of the solar system. This isn't the only hypothesis, but it seems to be the most popular one, that it was all born from a nebula that was formed by an exploding supernova somewhere in the past, and that's where the time, excuse me, the time's a bit tricky perhaps. So it started with this rotating primordial dust cloud. Now I can understand how stars are made of gas. It's never quite explained where the dust comes from, is it? But anyway, and eventually, due to gravity and things like that, the dust particles condense, if that's the right word, into larger objects, and gravity pulls enough material to the center and it gets hot enough that the sun springs into life. The remaining particles form into these rings and then keep crashing into each other until we have the planets we know today. Is that what Brian Cox said yesterday?
No, I had a different theory yesterday. He talked about tendrils of dark matter, and where they cross is where stars or suns formed and ignited, which I hadn't heard before. But
no, that must be newer. Oh, that's interesting. Okay, yeah, that's good. Yeah. All right then. As I say, this is one of the hypotheses, perhaps we should say, because this explains quite a lot of the things we're used to, like the fact that all the planets go around the sun the same way and they're all spinning the same way and that kind of thing. So I'm thinking is that all the elements we've got must have been in that cloud. Perhaps that's too simple, but I don't think they were created by subsequent processes. And the only clue I got to that, again, was Mr. Cox saying that the early stars had quite short lives, only a few million years. So maybe there had been enough generations of stars and supernova to generate what we're used to seeing on Earth now. That got me thinking about, and then I stumbled on this. Now, I don't know if any of you have seen this before. As you know, I always like looking at a periodic table if I get a chance. And this one's coloured based on our current knowledge of where the elements were made, if you want to call it made. So I thought we'd just have a couple of minutes aside. Obviously, we could spend the whole morning talking about this, but it was interesting. I thought that I was quite happy with the fact that hydrogen and helium had mostly come from the Big Bang. But I've never heard of cosmic ray fission that appears to have produced boron and is that beryllium, that one?
Beryllium.
Yeah. Yeah.
And a little bit of lithium as well.
Yeah. And yeah, this is there are there's 100 little squares in each square. So that's supposed to give you the percentage of each process that we think was involved. So there's some that come from stars like our sun exploding at the end. That's all those green bits, and some of the heavier elements as well, because I think I must have had a simplistic view that you needed a bigger star to make a heavier element, but clearly it's not quite as simple as that. And lots of it's from merging neutron stars, which does sound like it would be an exciting event.
Couldn't we also get some from where elements, we've got the bigger elements which are then broken down?
Yes, yeah. And I'm not quite sure how that's represented on here.
That's what I was looking for, to see where it came in. And
yeah, no, I don't know if this is like starting conditions or where we're at now. What I can do, if you wish, is send you a pointer to a certain Professor Jennifer Johnson, who designed this, and she's got a blog that explains quite a few things, including we still don't know everything yet. Which you could say about science, couldn't you?
Yeah.
That's why we like it.
Yeah, indeed.
So as I say, just a little aside there. Back to the birth of the Earth. So these sticky collisions in our orbit carried on. I'm going to stick with my theory for this morning, Pat.
Yeah, good.
Carried on in the orbits of the planets, and again the simple explanation in the book says that the intense radiation from the sun drove the liquids and gases off the planets that were closest, so they ended up being rocky planets, and the outer planets were more gassy. So that's all all fine, but what I thought was quite interesting was that the so-called giant impact. So this happened really early on, in about the second week of January, apparently. We think something really large hit the forming Earth and turned the whole thing into a fireball. And what it's given us was the metal core, because the whole Earth became molten, it caused the heavier elements to end up in the center and the lighter elements on the surface. A bit was flung out, which gave us the moon, and it's also the impact that gave us the tilt of the axis of rotation. So the seasons, and I've seen it argued elsewhere that the moon and the seasons perhaps are one of the things that promoted life. So it's quite a significant effect, if you like.
Do other planets not have the tilt?
Yes, some do. I think is it Neptune that's famous for being at 90 degrees. And I read somewhere recently that they think that was to do, and this is why this is perhaps a theory rather than anything else. That was to do with its moons migrating. I think this week they were talking about Titan, is it, being thrown out of Jupiter's orbit? It may fly out or it may crash in. It's going to take billions of years, so don't panic. But that could also contribute to the tilt of planets, what the moons do. So yeah, I think perhaps we should look at this as a kind of overview. I'm not sure what really goes on is much more complicated. But I just thought I'd heard of the giant impact, but I hadn't really considered its importance, if you like. And then after that, there was a lot of volcanism going on, and the rock that did end up on the surface, because it was cooler, started to solidify into what they've called a scabby crust. And also these scabs, the solid parts slowly coalesced to form larger chunks, which were called cratons. And they're the beginnings of the continents that we've got now. And still under some of our larger continents, there is evidence of the original cratons from 4 billion years ago. Still see basically the continental crust is much deeper than it is elsewhere. So there you are, fiery birth. And it's given us this, the metal inner core, which is still quite hot. The inner core is solid, and then the outer part is liquid, and it's the currents in that liquid that give us our magnetic field, which is made of much of in the book because it's a book for walkers. The crust is cold and quite brittle. Well, it's rock. It's solid rock. We're used to that because that's the bit we walk around on. But it is very thin. You know, they say it's think of it like a skin on an apple rather than the skin on an orange.
By thin, how thick is that?
Next slide.
Oh, okay.
Good question, Jane. Next slide. It's about 5 to 10 kilometers, I think, under the ocean's crust, oceanic crust. So that's compared with 6 and a bit thousand. It's quite thin. And then in between, we've got this sticky part called the mantle, which has convection currents in it, driven by the heat from the inner core. And the mantle's made up of 2 parts, the lithosphere and the asthenosphere, which you'll see in a minute how they interact. Okay, so far?
Mm-hmm.
Okay, so we look at the lithosphere because that's the bit that's of most interest to us, I guess. So the crust is, there's sort of 2 types basically. There's the oceanic crust. So the crust underneath the ocean is thinner than the continental crust, but even the continental crust isn't that big. It's 30 or 40 kilometers. So the oceanic crust, because of the way it's formed, which we shall see in a minute, is mostly basalt and gabbro, which are igneous rocks. Again, we'll talk about rock types in a minute. Whereas continental crust, as we know, has got all the other rock types that we know and love. At the top, I know this is something I hadn't really realized before. I thought the crust was the crust and the mantle was the mantle, but it turns out the top part of the mantle is solid rock like the crust. And that's why it's called the lithospheric mantle. And that's made of a rock called peridotite. It's difficult to pronounce anyway. Peridotite, I guess you'd call it. And the man in the book said the way to think about this is it's like cold tarmac. So it is solid. It's exactly the same rock that the asthenosphere is made of, and that's like warm tarmac. So it does move, but it moves very slowly, the lower part of the mantle. For example, the heat plumes, you get plumes of heat rising up from the core. So to get from the core to the surface could take 100 million years. So it does move very, very slowly. but because we've had billions of years, there's still time, if you like. And that's just a snapshot of a local bit of the Earth's surface. We'll talk in a minute about what's going on in that. The mechanisms, basically the heat from the center drives the convection currents in the mantle, and that's what causes the movement of the crust on the surface. And the movement of the crust on the surface, with a bit of weathering and a few other things, are what's created all the different rock types that we see, that we find. So I thought now would be a good time to talk about rock types. You've all heard of these three rocks. This is like favorite pub quiz question, isn't it? Mm-hmm. So yeah, basically igneous are formed from magma. The important thing about magma is it's molten rock of any kind. It's not the mantle coming out. It's the heat from the mantle melting the crust. So it's mostly crustal rocks, and therefore the makeup of the igneous rocks depends on which bit of crust you're melting. It's easy to think, oh, it's the mantle coming out and it's all the same, but it's not quite as simple as that. Sedimentary, well, it's stuff washed down from mountains and laid in estuaries, or it's made of small sea creatures or plants or things like that that leave behind rocky remains. Metamorphic is either of the above that's been subjected to heat and pressure, and we'll see later on where that goes on mostly. So now I thought we could perhaps have a bit of a quiz. What rocks can you think of that are igneous? Would you say?
All the stuff coming out at the moment in that island in wherever it is, all that lava.
Yep. Yep. I was thinking
type called R.
More of what rock types would we consider? You know, like let me give you some examples. They're all igneous, so they were formed of melting magma, cooling magma and solidifying magma. And I've chosen those three because although they're the same rock, they're made of the same minerals, they have different appearance and different qualities due to how swiftly the lava cooled. If it cools slowly, there's time for big crystals to grow, and you get rock with quite large grains like granite. Slightly quicker, you get basalt. And if it's quenched, you get obsidian, which is kind of glass-like, very fine grain. So it's to do with the conditions when the magma's cooling.
So you could also add to that pumice.
Yes. Yeah. Yeah.
But that's a very light rock that floats in the sea.
It is. It is.
Yeah, we've seen that in New Zealand with the rocks floating around in the sea.
In a minute, when we do show us your, let's look at your rocks. We probably have a piece of that somewhere, I expect. Yeah. So pumice is the stuff that's thrown out that's very light and bubbly. It's kind of like the froth on a can of Coke, and then that cools and it traps the gas inside, which makes the bubbles. And yeah, as you say, very light. Okay, can you think of any sedimentary rocks?
Sandstone, limestone.
Yeah. That was good. So I've split these into the different types roughly. So sandstone is, well, what it says, it's eroded stone from somewhere else that's been washed down rivers and then compressed over the years by overlaid rocks and turned to stone. So it's completely mineral. chalk and flint are the ones that are made of sea creatures. So some sea creatures have shells made of mostly calcium carbonate, so that forms the chalk. The others that have got silica in their shells end up forming the flint, often found together, of course. Plants, if you squash plants down, you get peat to start with, and after a while, if you squash them for a bit longer, you end up with coal. So that's organic again. And the last class of sedimentary rocks are salts that are formed by evaporation of lakes, for instance, and gypsum is an example of that. So that's left another class, metamorphic ones. Any guesses there?
Shale?
Sorry, Malcolm?
Shales?
Yes. Yeah. Yeah.
There's ones in Cornwall. And I'm trying to remember the name. I've forgotten everything I used to know.
All right. Okay. We don't want to make this painful. Let's look at the ones I've chosen. I mean, there are lots, of course, but it's slate.
Wales.
Yeah, slate is interesting because it shales, like Malcolm was saying. This is kind of mudstone, which is like fine sandstones that have been heated and squashed a bit. And one of the first things that happens is that some minerals form into like plates, very flat plate-like shapes. And slate, of course, is an obvious example. It makes it very useful to us because you make thin sheets of it. Marble is what happens if you expose limestone to limestones to heat and pressure and so on. And nice, nice, you get it in Lewis, don't you? I think that might be igneous rock that's been subjected to pressure. Sorry, I forget exactly that one. So lots of different rock types anyway. And sorry?
Diamond would be metamorphic, wouldn't it?
Yes. Yeah. Yeah.
Another one went through my mind a moment ago, and I've now forgotten what it said.
All right. Well, we can have a. How are we doing? How's the time going? All right. Yeah. Yeah. I should have said at the beginning. Sorry, I should have said because we all do know about this subject. Do feel free to interrupt me if you wish. We can have a talk about any of this. So this then begs the question: well, what are rocks made of exactly? Oh no, it doesn't. That'll be next. You can see I've rehearsed this well, can't you? So, I thought I'd just show you the rock cycle. Again, because this is another nice picture in the book, I thought. So just briefly with this, let's start off with magma. So we start off with molten rock being exuded from a volcano or something. And then, I can't keep the arrow working. That through solidification, that forms igneous rocks, as we know, and then they get uplifted or they get exposed through weathering and end up on the surface. So at the top, this green box are the rocks that we see on the surface. So that's how one sort of rock is formed, if you like. Then they get eroded maybe through sedimentation and burial and become sedimentary rocks, which can also get uplifted again and end up on the surface, the green arrows. Either of these sorts of rocks can be turned into metamorphic rocks by temperature and pressure, and again get exposed on the surface. And then through other processes, all of them can get melted and turn back into magma. So that's a kind of simplified picture of the rock cycle. And the important thing to note is it's still going on now. You know, it's not something that only happened in the past. It's just that it doesn't really do it at human timescale, so we don't notice it too much.
It does when you see volcanoes.
Yeah, yeah, and things like erosion you can see, can't you?
Yeah.
Yeah, and things melting and yeah. So now we're going to see what rocks are made of. Rocks are made of minerals, as I'm sure you knew. Small grains. There are around 4,000 naturally occurring minerals, or things that we define as minerals anyway. So I've given you a couple of examples there. Quartz is silicon dioxide, I suppose you'd call that, and feldspat's got potassium, aluminium, silicon, and oxygen in. Lots of rocks have got silicon in. That's quite a numerous element. And the way they look and the ingredients, if you like, of these minerals depends on how they were formed and to some extent what's happened to them since. When we go to the rock shop and we buy minerals, we look for one that's got nice crystals in, don't we? You know, I'm sure you've got some to show me, those nice geos with all the crystals growing inside. But most rocks are formed in conditions where there isn't room or time, or it's just not the right conditions for the crystals to grow properly, which is why we term them grains. And there's some examples there from kitchen worktops of marble, I guess they would be, wouldn't they, or granite worktops. But sometimes you get quite big crystals, as in the cave at the top with the men in it. It's a famous cave in Mexico with these selenite crystals in it, giant ones, which must have grown very, very slowly in just the right conditions. So yeah, rocks and minerals, again, a little bit of an aside from what we're doing, but next we're going to talk about plate tectonics. So did you want to discuss your rocks you brought along now, or should we leave that to the end?
Not too worried, which
Any preferences? Do you want me to carry on now in full flow?
Yeah, you carry on. Yeah, now you're in flow.
All right. Okay. So plate tectonics, something else you've heard of as well. As you can see from these dates, suspected for a long time, Abraham Ortelius, famous map maker, made early maps and atlases. And it occurred to him when looking at the, and of course, this was when the Earth, you know, the surveys of the Earth's surface were a bit more rudimentary than they are now, when we've got satellite pictures. But even based on those, he could see that it looked like they fitted together. Benjamin Franklin had a theory, as he did on lots of things. That's a quote from his. He even suggested that the surface might be floating on a fluid. But the first person to really come up with the idea was the German Wegener, and he was the man that talked about Pangaea, a supercontinent, which was the last. There'd been supercontinents before, but this was kind of the last one. And one of the things, and he also termed the term continental drift. So it couldn't be explained how the continents had moved apart, but the evidence was mounting that they probably had. And one of the things that Wegener did was he plotted where fossils were found, and that's what the coloured lines on that map indicate. And he noticed the commonality, you know, that the lines of fossils would line up if you put the continents back together, and that was thought to be another bit of evidence towards it. And I can remember when I was at school, this was very new. They were just talking about tectonics in the 60s. And again, it wasn't fully explained how it worked. So partly it leapt forward because of studies of the world during and after the war. That was when they discovered the mid-Atlantic ridge, for instance. And by measuring the magnetism in the rocks, you've probably seen this picture, they found that in parallel with the ridge, there were strips of rock that were magnetized in different directions. And this was at the same time when we were learning that the poles had changed places from time to time during the Earth's history. And they'd left that signature in the rocks. So that also gave a timescale to the so-called seafloor spreading. So all these things came together. And by the 70s, we had this model of what actually moves the continents. So you get the heat from the mantle causing a volcano, basically melting the oceanic crust. Initially, it causes a thinning of the crust, which causes the crust to lift up and then drift away from the bump, if you like, naturally. And this example is just the Atlantic, which at the moment is expanding and pushing America and Europe apart. Okay.
Mm-hmm.
So what I've got now is just a few pictures of the different movements, but first let's look at the plates themselves. So these are the main tectonic plates. The red lines are where they're moving apart. The black lines are where they're pushing together. The green ones, that are called transform, that's when they're sliding past each other, because actually, because the Earth's a sphere, they don't kind of move in straight lines. They tend to rotate. The African plate, for instance, is rotating, which causes the sliding effect in certain places. And I'm going to have to resort to the book now to tell you what those numbers mean. Excuse me for a minute. So if we start with 1 here in Africa, that's the Rift Valley. So that's moving apart as the 2 separate African plates, the Nubian and the Somali plate, move apart. The Red Sea likewise, number 2. So the Rift Valley and the Red Sea are getting wider. They're like the Atlantic was a long time ago. They will become an ocean eventually. 6, top of Africa, this is called a closing ocean. So the Mediterranean is closing slowly, will disappear because the African plate is moving northwards into the Eurasian plate. So that's going to squeeze out the sea. Over here at 7, where the Indian subcontinent's charged into Asia, that's already happened. So here we've got 2 continents colliding at number 7. And of course, that's pushed up the Himalayas and continues to do so. The Himalayas are growing. That's even measurable, that growth. What else have we got that's interesting on there? Number 8, we hear a lot about, don't we? The US East Coast, the San Andreas Fault and so on. So that's a so-called transform. That's sliding because the Pacific plate's rotating and causing a sliding effect along the fault.
And all around the Pacific is the Ring of Fire.
That's right, yeah. So at the edge, at these plate edges, you get the volcanic activity, which we'll see in a minute.
The black lines.
Yeah, well, you get it at both. You get it where the plates are moving apart, but also because of the heat and the pressure generated when the plates move together, that also creates volcanic activity. So the black line and the red line. Yes, and so area 4 is a subduction zone. We'll learn about that in a minute, but you can probably guess that that means one plate going under another one. Oh. And that's favourite for creating earthquakes, volcanoes, all that kind of stuff. And of course, these countries here are all associated with that. One other thing to mention. Okay, it doesn't show this one, but down this line here by number 4, where you get the plates colliding, you often get a trench. And of course, this one in the Pacific here is the famous deepest trench, the Marianas. But there's also a trench in the Atlantic here at number 9, the Romanche Trench.
And what's the interesting little deviation off the west coast of North America that I'm not going to try and pronounce? No, the west coast. There.
Oh, this one.
No, the red, the one.
Oh, here.
And the
Yeah.
Puka.
Wanda Pucha.
You want the future? Well, that's. Oh, I'm glad you asked me that.
Sorry. It's just I was just intrigued that it's a very tiny.
It is
in the big picture
Um,
things. Off, where the my son and his family have training because of what might go on land there, but there's just off the coast of San Francisco.
That's a good question, Malcolm. And in actual fact, we can touch on that because I've now just remembered what it really is. It's a complication with the sliding fault, but it's like a special case, if you like, and it's quite an interesting special case. So we will mention it.
Okay, all right.
If I could ask you to just wait for a bit.
I will. I'll be patient. Yes.
Yeah. Thanks. I thought you were going to ask about this strange printing, and that's because I've combined two pictures out of the book which didn't really fit together, but more or less got away with it.
Yeah.
So that's the big picture, as you might say. The arrows, of course, indicate the direction of movement and also the speed. Bigger arrows, they're moving quicker. So let's see what happens at these joins then. We'll start off with the divergent ones. So this is where the seafloor spreading is going on. And just going down the pictures from the top. The first thing that happens is you get this so-called super plume. So you get this hot spot in the mantle, which causes the crust to thin. It melts the crust. So up here where it says number 1, these numbers, it causes the crust to melt, and you get these red blobs of the volcanic activity. And obviously the ones with the ash coming out are actual volcanoes. So it causes, it melts the rocks, it causes volcanoes, and it also causes a split to occur. So this is exactly what's going on in the African Rift Valley now. And I haven't included it, but if you can see the colors, the yellow, can't get my arrow doesn't want to go in front. Why not? Here we are. The yellow parts in here are a sedimentary rock being formed. It just gets washed down from the cliff faces on each side. Okay, Peter. The red, obviously, the red blobs here are igneous rocks being formed, and the other volcanic activity up here is forming other rocks. So these pictures also try to explain how the different rock types are formed by these movements. So that's how it starts. You get volcanism, you get sediments. As that progresses, the rift basically widens as the two continents move apart. And that's the situation in the Red Sea. It's got that little bit further. We've still got the volcanic rock activity in the middle. We've got new crust being formed now. So the magma that's coming out of that ridge cools on either side and basically creates new crust. That's what creates the new crust as the continents move apart. The sedimentation carries on as it does at the bottom of any sea. So basically you're getting sedimentary and igneous rock created there. This continues till we get to the situation we've got with the Atlantic Ocean, which is really a wider version of the same thing. And all that sort of dark greenish line is the new crust that's being formed. Because a lot of time has now passed, there's been a lot more sedimentation off the continents into the sea. So in the coastal areas, you get your sedimentary rocks forming. And in the little kind of aside there, the little cutout is to point out that the join between the oceanic crust and the continental crust is not a plate boundary. It's a passive margin. You get faulting because of the forces involved, but you're not got any volcanism going on there, for instance. All right.
Mhm.
Well, that's what's happened. That's a very swift view of a divergent plate boundary. But because the surface of the Earth is limited, somewhere else there has to be a convergence going on. And what happens here is, again starting at the top, one of the plates is forced underneath the other one. And this is where the metamorphic rocks are formed, because this generates quite a lot of heat and pressure, enough to melt the crust. So the crust melts, and you get volcanic activity on the top plate, the one that's riding over, and the magma that comes out of there is composed of whatever the crust was made of that got forced underneath. So you've got, in this case, you've got what they're calling ocean-to-ocean subduction. So this is what's going on in the Philippines. You've got oceanic crust, which, as we know, is mostly basalt, being forced underneath, but some of the sediment gets pulled under as well. So where the M is, where the white M is, I don't know if you can see that, but it's a little white M there, by number 3. That's where the metamorphic rocks are being formed because of that temperature and pressure we talked about. That's where it is. It's not always, this doesn't always go on in the oceans. Sometimes you get, in a way, an easier one to understand, I think, is the oceanic plate being forced under a continental plate, such as is going on in South America, pushing up the Andes, more volcanic activity. The same kind of idea, but what happens when you've got solid land rather than being in the ocean. In the ocean, the volcanic activity causes islands to be formed, volcanic islands. It just pushes the seabed up. Eventually, it pops out through the surface. This continues until the two continents come together. So where it's being pushed down and elsewhere in the world, there's a divergent fault pushing the continent. The continent is dragged along, if you like, by the oceanic crust that's going underneath. So eventually the continents collide, like as in the bottom picture. So that's quite a violent thing. You get all sorts of, you get a lot more metamorphic activity. Notice that some of the volcanic activity doesn't reach the surface. The magma cools. It's not all volcanoes. Sometimes, and they call that plutonic. I'm not quite sure why. So you can get great, what they call sills, where there's soft rock or gaps in the rock that it can form in, and then it solidifies before it gets to the surface. So that's another kind of volcanic rock that is formed. And eventually, these two continents weld together and form a new one. Again, this is India joining Asia. Okay, now we better mention the other one, the transform boundaries. So there's two sorts basically of transform boundaries. I'm going to do the number 9. I'm going to do the second one first because it's not simply, these plates don't simply move in straight lines. They're sliding and twisting and bending. You get sliding joins as well. So the mid-ocean ridge, although we think of it as a nice straight line of volcanoes, actually it's a bit jagged. And sometimes, like this example here between the South American plate and the African plate, you get a sliding movement. So the red lines are a spreading movement, but the green ones are a sliding movement. Now, if we go back to the top picture, this is what's happening on the west coast of America. Yuan Lafusha, perhaps. And it's a kind of special case because it's where what was a mid-oceanic ridge has arrived at the continent. And because of the different shape, it causes, basically, it just complicates the movement. So you get a mixture of squashing and sliding going on. And I guess that's what makes that fault a bit more jumpy, if I can describe it like that.
Yeah, the San Andreas fault is jumpy, so it's having its impact on the major fault line, the
Yes.
San Andreas. Yeah. So again, that's what gives the instability. That's interesting. Yeah.
I thought that was good because it never struck me that a mid-oceanic ridge must eventually collide with the continent, and of course it's not a nice smooth transition like it.
No.
And the last sort of movement is you can get hotspots underneath the plates. So this is just another hotspot, a kind of narrow hotspot, if you like, underneath the middle of the plate. And these in the Pacific are a good example, where you've got this hotspot which causes volcanic activity and it pushes up volcanic islands. But as the plate moves, it takes the islands away from the hotspot. So the volcanic activity stops and another volcano is formed. So you get this archipelago of islands, and Hawaii is a good example, where you've got islands that are no longer volcanically active and ones that still are. And then, of course, they get eroded to atolls and eventually just bumps on the seabed. So that's the I think that's all I've got to say about those plates. Very brief, but there we are. And that should explain all the rocks we've talked about. I couldn't really not mention volcanoes, especially after I watched Ian Stewart. They've repeated that BBC program called The Power of the Planet or something. He's an enthusiastic Scotsman who goes all over the world looking at things, and he talked about supervolcanoes. So I thought we ought to have some big numbers perhaps in this talk. So supervolcanoes are just big ones basically, and the most recent one was Mount St. Helens. It took 400 meters off the top of the mountain, 24-kilometer ash column in 15 minutes. 15 minutes. And there's a wonderfully called volcanic explosivity index, and it scored 5 on that, but this index does go up to 8.
That's American.
Oh, I'm sure it is, yeah, because they describe them as super colossal or something. Yeah. Oh no, mega colossal. Yeah. I mean, presumably awesome is at 9, but however, we've had bigger ones in the past. The one that we know a little bit about perhaps is Tambora in 1815, which they estimate to be 100 times more powerful than Mount St. Helens. And yeah, that was the deadliest, mainly because it caused famine, frost in the summer. You know, you probably read about it, The Year with No Summer. And it inspired Frankenstein, some of Turner's paintings, Byron's poem Darkness. So it perhaps had a psychological effect on us too, who knows. The one in Yellowstone has gone off a few times, but the last time was a mere 64,000 years ago, and that was really big. So big that they couldn't find the crater until they took a few steps back. They, not sure where this crater is, and then realized it was much bigger. And of course, it's due to do it again sometime. And then I've just included one more. There've been 7 that we know about in
Isn't the Yellowstone Park one linked with the San Andreas fault? Isn't it that they expect the whole thing to have a ripple effect?
It's possible. There's two magma chambers under Yellowstone. My geography is not quite good enough to picture where Yellowstone is. Is it in the middle somewhere, or is it?
Yeah, it's directly inland from San Francisco. Yeah.
Oh, okay, right.
My son drove there last summer.
Yeah. So it's part of that plate movement. Yes, I guess. Yeah. It's another volcano caused by that. And the other one that caught my eye when I was reading about them was the Toba, again in Indonesia. So it's not somewhere you want to be, at least not for a long time anyway. And they think it may have caught, may have human, the human life obviously was considerably different 75,000 years ago, but there seems to be a bit of a bottleneck in the genetic into sort of DNA studies of these prehistoric folk, and where they think the population of the world might have got down to a few thousand. And this it's been this conjecture that this may have been the cause of that. But I just thought that was an interesting kind of angle on it. Last bit of plate tectonics is that this fellow Wilson, John Wilson, again in the 1960s, suggested that this was another cycle, a slow cycle, granted, but another cycle. And that's what gave us the idea that Pangaea wasn't the first supercontinent. And in fact, there are others now that are named anyway. Because I think as we learn more about the placement of rock types in different parts of the world, it's easier to kind of backtrack and work out the movements that have gone on. If we do get to talk about the UK, we'll find that it's been on a long journey around the world. So yeah, there's a cycle and the different places in it where the different rock types are formed. And that's me lot.
Very good.
Next time, well,